You can never see anything enter
I'll give it a
a
chance.
black hole.
Play this horror game. Link.
Imagine you trap your nemesis in a rocket ship and blast him off towards a black hole. He looks back at you, shaking his fist at a constant rate. As he zooms in, gravity gets stronger, so you would expect him to speed up. But that is not what you see. Instead, the rocket ship appears to be slowing down. Not only that, he also appears to be shaking his fist slower and slower. That's because, from your perspective, his time is slowing down. At the very instant when he should cross the event horizon, the point beyond which not even light can escape, he and his rocket ship do not disappear. Instead, they seem to stop, frozen in time. The light from the spaceship gets dimmer and redder until it completely fades from view. This is how any object would look crossing the event horizon. Light is still coming from the point where he crossed, it's just too redshifted to see. But if you could see that light, then in theory you would see everything that has ever fallen into the black hole frozen on its horizon, including the star that formed it. But in practice, photons are emitted at discrete intervals, so there will be a last photon emitted outside the horizon,
xQc,
and therefore
please,
these images will fade after some time.
This is just one of the strange results that comes out of the general theory of relativity, our current best theory of gravity. The first solution of Einstein's equations predicted not only black holes, but also their opposite, white holes. It also implied the existence of parallel universes and even possibly a way to travel between them. This is a video about the real science of black holes, white holes, and wormholes.
The general theory of relativity arose at least in part due to a fundamental flaw in Newtonian gravity. In the 1600s, Isaac Newton contemplated how an apple falls.
You know, this is all theories and theoretical physics or whatever, right? It wasn't at one point the atom bomb the same thing, it's just a theory and just math or whatever, and then they did it and it actually worked. So they kind of does that kind of give you hope that, like, if things check out, if you were to actually do it, it checks out.
Falls to the ground, how the moon orbits the Earth and Earth orbits the sun, and he concluded that every object with mass must attract every other. But Newton was troubled by his own theory. How could masses separated by such vast distances apply a force on each other? He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has a competent faculty of thinking could ever fall into it. One man who definitely had a competent faculty of thinking was Albert Einstein, and over 200 years later, he figured out how gravity is mediated. Bodies do not exert forces on each other directly. Instead, a mass like the sun curves the space-time in its immediate vicinity. This then curves the space-time around it, and so on all the way to the Earth. So the Earth orbits the sun because the space-time Earth is passing through is curved.
Masses are affected by the local curvature of space-time, so no action at a distance is required. Mathematically, this is described by Einstein's field equations.
Can you write down the Einstein field equation?
This was the result of Einstein's decade of hard work after special relativity. And essentially what we've got in the field equations, on one side it says, tell me about the distribution of matter and energy. The other side tells you what the resultant curvature of space-time is from that distribution of matter and energy. And it's a single line. It looks like, oh, this is a simple equation, right? But it's not really one equation. It's a family of equations. And to make life more difficult, they are coupled equations, so they depend upon each other. And they are differential equations, so it means that there are integrals that have to be done, So there's a whole bunch of steps that you need to do to solve the field equations.
To see what a solution to these equations would look like, we need a tool to understand space-time.
So imagine you're floating around in empty space. A flash of light goes off above your head and spreads out in all directions. Now, your entire future, anything that can and will ever happen to you, will occur within this bubble, because the only way to get out of it would be to travel faster than light. In 2 dimensions, this bubble is just a growing circle. If we allow time to run up the screen and take snapshots at regular intervals...
Yeah, but is it going forever? Is light in... Oh yeah, because it's in space.
Intervals, then this light bubble traces out a cone, your future light cone. By convention, the axes are scaled so that light rays always travel at 45 degrees. This cone reveals the only region of spacetime that you can ever hope to explore and influence. Now imagine that instead of a flash of light above your head, those photons were actually traveling in from all corners of the universe, and they met at that instant and then continued traveling on in their separate directions.
That's how it is every second, no?
Well, in that case, then into the past, these photons also reveal a light cone, your past light cone. Only events that happened inside this cone could have affected you up to the present moment. We can simplify this diagram even further by plotting just one spatial and one time dimension. This is the space-time diagram of empty space. If you want to measure how far apart two events are in space-time, you use something called the space-time interval. The interval squared is equal to minus dt squared plus dx squared. Since spacetime is flat, the geometry is the same everywhere, and so this formula holds throughout the entire diagram, which makes it really easy to measure the separation between any two events. But around a mass, spacetime is curved, and therefore you need to modify the equation to take into account the geometry.
This is what solutions to Einstein's equations are like. They tell you how spacetime curves and how to measure the separation between two events in that curved
This
geometry.
is impossible. Chat.
Einstein...
Wouldn't you have to know all the bodies that are impacting gravity, all of them, and calculate all of them at the same time? What if there's something that you don't see? Chat, what if everything that we ever know of, we're also spinning it, and that is in a galaxy that's also spinning it, and that's also spinning it, and we're also spinning in a spinner, and it is
published his equations in 1915 during the First World War, but he couldn't find an exact solution. Luckily, a copy of his paper made its way to the Eastern Front, where Germany was fighting Russia. Stationed there was one of the best astrophysicists of the time, Karl Schwarzschild. Despite being 41 years old, he had volunteered to calculate artillery trajectories for the German army.
That sounds kind of fun.
At least until a greater challenge caught his attention. How to solve Einstein's field equations.
Schwarzschild did the standard physicist thing and imagined the simplest possible scenario, an eternal static universe with nothing in it except a single spherically symmetric point mass. This mass was electrically neutral and not rotating.
Chat, I don't want to be dark, Chat, but if you do like math and you do a bunch of theory and shit and a bunch of like only numbers, I just said it's fun because like, even though I get it's war and it's boom and explosions, you get to see the numbers affect in real time. You get to see.
Since this was the only feature of his universe, he measured everything using spherical coordinates relative to the center of this mass. So r is the radius, and theta and phi give the angles. For his time coordinate, he chose time as being measured by someone far away from the mass, where spacetime is essentially flat. Using this approach, Schwarzschild found the first non-trivial solution to Einstein's equations, which nowadays we write like this. This Schwarzschild metric describes how spacetime curves outside of the mass. It's pretty simple and makes intuitive sense. Far away from the mass, spacetime is nearly flat, but as you get closer and closer to it, spacetime becomes more and more curved, it attracts objects in, and time runs slower. Schwarzschild sent his solution to Einstein, concluding with, "The war treated me kindly enough, in spite of the heavy gunfire, to
time runs slower, or is it just takes more time overall, and therefore it
allow me to get away from it all and take this walk in the land of your ideas." Einstein replied, "I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution to the problem in such a simple way." But what seemed at first quite simple soon became more complicated. Shortly after Schwarzschild's solution was published, people noticed two problem spots. At the center of the mass, at r equals 0, this term is divided by 0, so it blows up to infinity, and therefore this equation breaks down and it can no longer describe what's physically happening. This is what's called a singularity. Maybe that point could be excused because it's in the middle of the mass, but there's another problem spot outside of it. at a special distance from the center, known as the Schwarzschild radius, this term blows up. So there is a second singularity. What is going on here? Well, at the Schwarzschild radius, the spacetime curvature becomes so steep that the escape velocity, the speed that anything would need to leave there, is the speed of light. And that would mean that inside the Schwarzschild radius, nothing, not even light, would be able to escape. So you'd have this dark object that swallows up matter and light. A black hole, if you will.
But most scientists
Chad,
doubted
can you make this faster? Can you go fast in the speed of light?
that such an object could exist, because it would require a lot of mass to collapse down into a tiny space.
Then the only way to leave that is impossible then, right? So how could we... nothing
How could
leaves.
that possibly ever happen?
So what happens when it's filled?
Astronomers at the time were studying what happens at the end of a star's life. During its lifetime, the
Oh, it
inward force of
grows.
gravity is balanced by the outward radiation pressure created by the energy released through nuclear fusion. But when the fuel runs out, the radiation pressure drops, so gravity pulls all the star material inwards. But how far? Most astronomers believed some physical process would hold it up. And in 1926, Ralph Fowler came up with a possible mechanism. Pauli's exclusion principle states that fermions, like electrons, cannot occupy the same state. So as matter gets pushed closer and closer together, the electrons each occupy their own tiny volumes. But Heisenberg's uncertainty principle says that you can't know the position and momentum of a particle with absolute certainty. So as the particles become more and more constrained in space, the uncertainty in their momentum, and hence their velocity, must go up. So the more a star is compressed, the faster electrons will wiggle around, and that creates an outward pressure.
And then what about boom?
This electron degeneracy pressure would prevent the star from collapsing completely. Instead, it would form a white dwarf with a density much higher than a normal star. And remarkably enough, astronomers had observed stars that fit this description. One of them was Sirius B. But the relief from this discovery was short-lived. 4 years later, 19-year-old Subramanian Chandrasekhar traveled by boat to England to study with Fowler and Arthur Eddington, one of the most revered scientists of the time. During his voyage, Chandrasekhar realized that electron degeneracy pressure has its limits. Electrons can wiggle faster and faster, but only up to the speed of light. That means this effect can only support stars up to a certain mass, the Chandrasekhar limit. Beyond this, Chandrasekhar believed not even electron degeneracy pressure could prevent a star from collapsing. But Eddington was not impressed. He publicly blasted Chandrasekhar, saying, "There should be a law of nature to prevent a star from behaving in this absurd way."
And indeed, scientists did discover a way that stars heavier than the Chandrasekhar limit could support themselves.
He was wrong.
When a star collapses beyond a white dwarf, electrons and protons fuse together to form neutrinos and neutrons. These neutrons are also fermions, but with nearly
Nutrients.
2,000 times the mass of an electron, their degeneracy pressure is even stronger. So this is what holds up neutron stars.
There was this conviction among scientists that even if we didn't know the mechanism, something would prevent a star from collapsing into a single point and forming a black hole. Because black holes were just too preposterous to be real.
The big blow to this belief came in the late 1930s, when J. Robert Oppenheimer and George Volkoff found that neutron stars also have a maximum mass. Shortly after, Oppenheimer and Hartland Snyder showed that for the heaviest stars, there is nothing left to save them when their fuel runs out. They wrote, "This contraction will continue indefinitely." But Einstein still couldn't believe it. Oppenheimer was saying that stars can collapse indefinitely, but when Einstein looked at the math, he found that time freezes on the horizon, so it seemed like nothing could ever enter.
Why would they know that?
Suggested that either there's something we don't understand, or that black holes can't exist.
But Oppenheimer offered a solution to the problem. He said, to an outside observer, you could never see anything go in, but if you were traveling across the event horizon, you wouldn't notice anything unusual and you'd go right past it without even knowing it. So how is this possible?
We need a space-time diagram of a black hole.
Chad, won't you rip apart?
On the left is the singularity at r equals 0. The dotted line at r equals 2m is the event horizon. Since the black hole doesn't move, these lines go straight up in time.
Chat.
Now-
Chat, even the difference, a slightly bit of speed from one place to another, if you go towards it, you would rip.
Now let's see how ingoing and outgoing light rays travel in this curved geometry. When you're really far away, the future light cones are at the usual 45 degrees. But as you get closer to the horizon, the light cones get narrower and narrower, until right at the event horizon, they're so narrow that they point straight up. And inside the horizon, the light cones tip to the left.
It's like a cylinder.
But something strange happens with ingoing light rays.
Chat, it's like calculus.
They fall in, but they don't get to r equals 2m. They actually asymptote to that value as time goes to infinity. But they don't end at infinity.
Like integrals.
Right? Mathematically, they are connected and come back in, and they're traveling in this direction. And this bothered a lot of people. This bothered people like Einstein because he looked at these equations and went, well, if nothing can cross this sort of boundary, then how could there be black holes? How could black holes even form?
So what is going on here? Well, what's important to recognize is that this diagram is a projection. It's basically a 2D map of four-dimensional curved space-time.
It's just like projecting the 3D Earth onto a 2D map. When you do that, you always get distortions. There is no perfectly accurate way to map the Earth onto a 2D surface. But different maps can be useful for different purposes. For example, if you want to keep angles and shapes the same, like if you're sailing across the ocean and you need to find your bearings, you can use the Mercator projection. That's the one Google Maps uses. A downside is that it misrepresents sizes. Africa and Greenland look about the same size, but Africa is actually around 14 times larger. The Gall-Peters projection keeps relative sizes accurate, but as a result, angles and shapes are distorted.
In a similar way, we can make different projections of 4D space-time
I actually knew
to
that.
study different properties of it. Physical reality doesn't change, but the way the map describes it does.
Guys, I've shown you guys this like 3 times in the past. You might remember, I showed you guys the maps and whatever.
He had chosen
You guys don't listen.
to put a particular coordinate system over space and have a time coordinate. And off you go. It's the most sensible thing to do, right?
People realize that if you choose a different coordinate system by doing a coordinate substitution, then the singularity at the event horizon disappears.
It goes away. That problem goes away. And things can actually cross into the black hole.
What?
What this tells us is that there is no real physical singularity at the event horizon. It just resulted from a poor choice of coordinate system. Another way to visualize what's going on is by describing space as flowing in towards the black hole, like a waterfall. As you get closer, space starts flowing in faster and faster. Photons emitted by the spaceship have to swim against this.
I get it. So the shape of it is all bad because it's just the wrong system to analyze it. So the black hole isn't actually doesn't look what it looks like. It's a tube.
Flow. And this becomes harder and
And you can
harder the
TP.
closer you get. Photons emitted just outside the horizon can barely make it out, but it takes longer and longer. At the horizon, space falls in as fast as the photons are swimming. So if the horizon had a finite width, then photons would get stuck here. Photons from everything that ever fell in. But the horizon is infinitely thin, so in reality, photons either eventually escape or fall in. Inside the horizon, space falls faster than the speed of light, and so everything falls into the singularity. So Oppenheimer was right. Someone outside a black hole can never see anything enter, because the last photons they can see will always be from just outside the horizon. But if you yourself go, you will fall right across the event horizon and into the singularity.
Now, you can extend the waterfall model to cover all 3 spatial dimensions, and that gives you this. a real simulation of space flowing into a static black hole, made by my friend Alessandro from ScienceClick. Later, we'll use this model to see what it's like falling into a rotating black hole.
What?
Now, I've never been sucked into a black hole, but sometimes it feels like it when I'm stuck on the phone with space-time maps.
If you take this map and transform it so that incoming and outgoing light rays all travel at 45 degrees like we're used to, then something fascinating happens. The black hole singularity on the left
I'm about to get a headache.
transforms into a curved line at the top. And since the future always points up in this map, it tells us that the singularity is not actually
The past!
a place in space. Instead, it's a moment in time. The very last moment in time for anything that enters a black hole. The map we've just created is a Kruskal-Zeker's diagram. But this only represents a portion of the universe, the part inside the black hole's event horizon and the part of the universe closest to
What about the things on the opposite side? Isn't that not the past?
it.
So what if you go into the black hole, right? As soon as you cross the halfway mark, you meet yourself, because it's you in the past going the other direction. No.
What we
Okay,
can
roll.
do is contract the whole universe, the infinite past, infinite distance, and infinite future, and morph it into a single map. It's like using the universe's best fisheye lens. That gives us this Penrose diagram. Again, light rays still always go at 45 degrees, so the future always points up. The infinite past is in the bottom of the diagram, the infinite future at the top, and the sides on the right are infinitely far away. The black hole singularity is now a straight line at the top, a final moment in time.
Ow.
These lines are all at the same distance from the black hole, so the singularity is at r equals 0, the horizon is at r equals 2m, this line is at r equals 4m, and this is infinitely far away. All of these lines are at the same time.
What's great about this map is that it's very easy to see where you can still go and what could have affected you.
For example, when you're here, you've got a lot of freedom. You can enter the black hole or
it's
fly off to
complicated.
infinity. And you can see and receive information from this area. But if you go beyond the horizon,
Chat.
you're
Chat, because guys, hold on. Guys, I have a question. Chat, I have a question. Chat. The light has to travel through something, right? Like space or whatever, right? So if it keeps going, right? It doesn't make any sense that the universe is infinite, because, I mean, it does. But like, it's going in space or whatever, so there has to be something. So there's always
only
more.
possible future is to meet the singularity. You can still, however, see and receive information from the universe. You just can't send any back out. Now, think about being at this point in the map. This is at the event horizon, and now your entire future is within the black hole. But what is the past of this moment?
That's why I said it.
Well, you can draw the past light cone, and it reveals this new region. If you're inside this region, you can send signals to the universe, but
map.
no matter where you are in the universe, nothing can ever enter this region, because it will never be inside your light cone. So things can come out, but never go in. This is the opposite of a black hole, a white hole.
A white hole is
What
a
color
black
is
hole
a
of the
white hole?
past.
I mean, it's going to be it's not going to have a color, right? It's going to be whatever's being spat out of it. It depends what's in there and gets thrown out. That's what you are going to see. So if it's got light in there, it's got mass in there, it's all going to be ejected. So the white hole kind of picture is the time reverse picture of a black hole. Instead of things falling in, things get expelled outwards. And so whilst a black hole has a membrane, the Schwarzschild horizon, which once you cross,
Dude,
you can't get back out.
If it's pushing things out really fast, right? At one point, there's what is it pushing it? Oh my! I just figured it out. It's the other side of the TP.
The white hole has the opposite. If you're inside the event horizon, you have to be ejected. So it kicks you out, kind of thing, right? Relativity doesn't tell you which way time flows. There's nothing in there that says that is the future and that is the past. When you're doing your mathematics and you're working out the behavior of objects.
I actually get that. I'm done. Last pause. I get it. YTP pushes, so the black hole sucks in, YTP pushes out like a TP, but you can never go back because you cannot go faster than light. So you can't fix the past.
Make a choice about
because the future is going away from you at max speed.
But mathematically, you could have chosen the other way, right? You could have had time point in the opposite direction. Any solution that you find in relativity, mathematically, you can just flip it and get a time reverse solution, and that's also a solution to the equations.
Now, we've been showing things being ejected to the right, but they could just as well be ejected to the left. So what's over there? This line is not at infinity, so there should be something beyond it. If we eject things in this direction, you find that they enter a whole new universe.
Another map!
One parallel to our own.
I get it. The way to fix your mistakes, if there's the past, is you go around through a shortcut and then it changes.
We can fall into this black hole, and somebody in this universe here could fall into this black hole in their universe, and we would find ourselves in the same black hole.
The only downside is that we'd both soon end up in the singularity.
I guess I'm just trying to understand where that universe appears in the mathematical part of the solution. Like, can you point to the part of the equation and be like, so that's our universe, and then these terms here, that's the other universe, or do you know what I mean? Like,
yeah. Well, it's coordinates, right? Imagine somebody, right, came up with a coordinate system for the Earth, but only the northern hemisphere. And you looked at that coordinate system, right? And you looked at it and you said, I can see the coordinate system, it looks fine, but mathematically, latitudes can be negative, right? You've only got positive latitudes in your solution. What about the negative ones? And they said to you, negative ones? No southern hemisphere, right? And you've got to go, well, the mathematics says that you can have negative latitudes. Maybe we should go and look over the equator to see if there is something down there. And I know that's a kind of extreme example because we know we live on a globe, but we don't know the full geometry of what's going on here, in the sense that Schwarzschild laid down coordinates over part of the solution. It was like him only laying down coordinates on the northern hemisphere.
Chad, this is a video chance to make me turn into a flat earther. Why is everything a globe? Everything is a globe, and I'm getting annoyed, chat. Everything that we know of, there's nothing else but globes. Chat, the dwarfs, the planets, the everything is a globe, right? It's all globe.
And other people have come along and said, hey, this is southern hemisphere. And more than that, there's two Earths.
Oh, because it's spinning.
That's why it's called maximum
so it's being
extension.
polished.
It's like, if I have this mathematical structure, then what is the extent of the coordinates that I can consider? And with the Schwarzschild black hole, you get a second universe that has its own independent set of coordinates from our universe. I want to emphasize, right? This is the simplest solution to the Einstein field equations, and it already contains a black hole, white hole, and two universes.
That's what you get when you push this map to its limits, so that every edge ends at a singularity or infinity.
And in fact, there's another little feature in here, which is that little point there where they cross. That is an Einstein-Rosen bridge.
To see it, we need to change coordinates. Now, this line is at constant Kruskal time, and it connects the space of both universes. You can see what the space-time is like by following this line from right to left. Far away from the event horizon, space-time is basically flat, but as you get closer to the event horizon, space-time starts to curve more and more. At this cross, you're at the event horizon, and if you go beyond it, you end up in the parallel universe. That gives you a wormhole that looks like this.
Yeah, TP.
So that is hypothetically how we could use a black hole to travel from one universe to another.
Hypothetically, because these wormholes aren't actually stable in time.
It's a bit like a bridge, but it's a bridge that is long and then becomes shorter and then becomes long again. And if you try to to traverse this bridge. At some point, the bridge is only very short, right? And you say, well, let me just cross this bridge. But as you start crossing the bridge and start running, your speed is finite, right? The speed of light, roughly. And then the bridge starts becoming stretching, and you never come out the other side.
Oh,
This
it's
pitching
a
off
bait.
always happens too fast for anything to travel through. You can also see this if you look at the Penrose diagram, because when you're inside one universe, there isn't a light cone that can take you to the other universe.
But wouldn't it like go exponential, less, but it would never hit zero?
The only way to do that would be to travel faster than light.
It would never hit
There
zero.
might be another way.
Schwarzschild solution describes a black hole that doesn't rotate. Yet every star does rotate, and since angular momentum must be conserved, every black hole must also be rotating. While Schwarzschild found his solution within weeks after Einstein published his equations, solving them for a spinning mass turned out to be much harder. Physicists tried, but 10 years after Schwarzschild's solution, they still
have
hadn't
to
solved
use
it.
the
10
equations
years
of the
turned
flat
into
earthers.
20, which turned into 40. And then in 1963, Roy Kerr found the solution to Einstein's equations for a spinning black hole, which is far more complicated than Schwarzschild's solution. And this comes with a few dramatic changes.
All right, bro.
The first is that the structure is completely different. The black hole now consists of several layers. It's also not spherically symmetric anymore. This happens because the rotation causes it to bulge around the equator, so it's only symmetric about its axis of spin. Alessandro from ScienceClick simulated what happens around this spinning black hole. Space gets dragged around with the black hole, taking you and the particles along with it. When you get closer, space gets dragged around faster and faster, until it goes around faster than the speed of light.
No!
You've now entered into the first new region, the ergosphere.
But we can't. 'Cause
No
we
matter
can't go
how
faster.
hard you fire your rockets here, it's impossible to stay still relative to distant stars. But because space doesn't flow directly inward, you can still escape the black hole. When you travel in further, you go through the next layer, the outer horizon, the point of
space
no
can.
return. Here, you can only go inwards.
That's what I said.
But as you get dragged in deeper and deeper, something crazy happens. You enter another region, one where you can move around freely again. So you're not doomed to the singularity. You're now inside the inner event horizon.
Only
Here,
space can do
you
that,
can
though.
actually see the singularity.
In a normal black hole, it's a point. But in a rotating black hole, it actually expands out to be a ring. And there are weird things happen with space-time inside the center of a black hole, a rotating black hole. But it's thought that you can actually fly through the singularity.
We need a Penrose diagram of a spinning black hole. Where before the singularity was a horizontal line at the top, here the singularity lifts up and moves to the sides,
Under the map,
revealing this new region inside the inner horizon. Here we can move around freely and avoid the singularity. But these edges aren't at infinity or a singularity, so there must be something beyond them.
Oh, dude.
Well,
dude.
when you venture further, you could find yourself in a white hole, which would push
This
you
is some
out
battle pass
into
bullshit
a
then.
whole nother universe.
You can have these pictures whereby you're in one universe, you fall into a rotating black hole, you fly through the singularity, and you pop out into a new universe from a white hole. And then you can just continue playing this game.
Extending this diagram infinitely far. But there is still one thing we haven't done: brave the singularity. So you aim straight towards the center of the ring and head off towards it. But rather than time ending, you now find yourself in another universe.
Chat, wouldn't it be faster to just go on the edges? Wouldn't you go faster if you go and use the
Range universe, one where gravity pushes instead of pulls. This is known as an antiverse.
If that's too weird, you can always jump back across the singularity and return to a universe with normal gravity.
It'd be faster.
And I know this is basically science fiction, right? But if you take the solutions of relativity at essentially at face value and add on a little bit, which is what Penrose does here. It says, oh look, these shapes are very similar. I can just stick these together. Then this is the conclusion that you get. Now we have effectively an infinite number of universes, all connected with black hole, white holes all the way through, and off you go to explore. But it'll be a very brave person who's the first one who's going to leap into a rotating black hole to find out if this is correct.
Yeah, I would not sign up.
But chat, I'm confused. Chat, to go faster than the speed of light, only space can do that. So even if you were to do that, you would still not go faster. You would still be limited by the speed of light, so it doesn't even matter.
So could these maximally extended Schwarzschild and Kerr solutions actually exist in nature? Well, there are some issues. Both the extended Schwarzschild and Kerr solutions are solutions of eternal black holes in an empty universe.
As you say, it's an eternal
Only the space,
solution.
nothing else.
So
right?
it stretches infinitely far into the past and infinitely far.
So the best you can do is pause time to nearly zero at like 0.0. When you're at the edge, it's like that's the best you can do is nearly stop
time. Future.
And
so there's no formation mechanism in there. It's just a static solution. And I think that is part of the reason why black holes are realized in our universe and white holes aren't.
Or might not be.
Or might not be. Well, I'm reasonably confident that they don't exist, right?
For the maximally extended Kerr solution, there's also another problem. If you're an immortal astronaut inside the universe, you can send light into the black hole. But because there's infinite time compressed in this top corner, you can pile up light along this edge, which creates an infinite flux of energy along the inner horizon.
Hold on, chat. I just realized that, chat. Even if you were to go into the past, it doesn't make any sense. Because as you would go towards the past, your thoughts are going in reverse, and then you're de-engineering and shit. No? Aren't you reverse thoughting?
This concentration of energy then creates its own singularity, sealing off the ring singularity and beyond.
My suspicion, and the suspicion of some other people in the field, is that this inner horizon will become singular and you will not be able to go through these second copies.
So all the white holes, wormholes, other universes, and anti-universes disappear. Does that mean that real wormholes are impossible?
In 1987, Michael Morris and Kip Thorne looked at wormholes that an advanced civilization could use for interstellar travel. Ones that have no horizons, so you can travel back and forth, are stable in time, and have some other properties, like being able to construct them. They found several geometries that are allowed by Einstein's general relativity. In theory, these could connect different parts of the universe, making a sort of interstellar highway. They might even be able to connect to different universes.
What if you can intercept the thing going across, right? And catch the past at the right time? Wasn't that how you go back in time?
The only problem is that all these geometries require an exotic kind of matter with a negative energy density to prevent the wormhole from collapsing.
This exotic kind of matter is really against the laws of physics, so it's I have the prejudice that it will not exist. I'm bothered by the fact that we say that the science fiction wormholes.
This guy's hairline got stuck in a black hole.
It's true, it's mathematically possible in the sense that it's some geometry that can exist, but Einstein's theory is not just geometries. It's geometries plus field equations. If you use the kinds of properties of matter that matter actually has, then they're not possible. So I feel that the reason they're not possible is very strong.
So, according to our current best understanding, it seems likely that white
you're
holes,
wrong.
traversable wormholes, and these parallel universes...
Well, you can't prove, with proof that he's right. My counter-argument is you're wrong.
...don't exist. But we also used to think that black holes didn't exist, so maybe we'll be surprised again.
I mean, we have one universe, right? Good. Why can't we have two?
Yeah, this is the same thing as, I knew this would be the same thing as in all the other theory videos. The video ends and you just feel like you know somehow less. And it's like a world makes less sense.